Chapter 6, Section 11, Assisted Protein Folding in Chaperones. Okay, there are some major chaperones in bacteria. Okay, these chaperones aid in folding. Okay, under textbook conditions, every protein should be able to fold itself. Okay, real world, reality, realistically, yeah, it doesn't always happen. So there's going to be these chaperone proteins that are going to basically shove the protein into its correct shape. If it can't be shoved into its correct shape, it's going to be tagged for recycling. In E. coli, DNA-K, DNA-J, GRO-EL, GRO-ES are key proteins that are going to aid in the correct folding. DNA-K, DNA-J are AT-dependent enzymes that slow polypeptide folding, slow it down so that it can get into the correct alpha helice beta sheet configuration that it needs to be, so that you don't have portions of it folding before, and interfering with the folding of other parts. Also, hopefully you remember from earlier lectures and earlier chapters, DNA-K, DNA-J, I think, oh, I'm sorry, this is chapter 7, sorry. Brain's going ahead. DNA-K, DNA-J will also be used as regulatory. They're slowing down the folding of a protein so it can't get into its final shape. Then they're also making it so that protein can't be the enzyme it needs to be. No shape, no function. It's made, the polypeptide's there, it just hasn't been able to fold into its final shape, thus have a function. Remove DNA-K, remove DNA-J from the equation, protein finally folds correctly, you now have a working enzyme. GRO-EL, GRO-ES, these aid in folding of the partially folded, not quite there proteins. If GRO-EL, GRO-ES can't do it, then they just target it, recycle, do over. Some of these chaperones are going to be types of heat shock proteins. Heat shock proteins are a collection of proteins that are activated when the cell is under stress. Why do they call them heat shock proteins? Well, that was the stress they found. They overheated the cells. I can't remember if they did it intentionally or if somebody screwed up. I think it was intentionally, just to see what would happen if you raise the temperature above, the Goldilocks zone for the cells. How will they respond? Do they all just die, or will they do stuff? Well, it turns out it activated certain signal pathways and turned on the expression of certain operons. If you have heat shock proteins, you also have cold shock proteins. Too hot, too cold. Goldilocks is when the cell wants to grow is the just right. Heat shock proteins are going to come into play, and they're going to try to help fold denatured proteins. Proteins that, because of the slightly increased temperature, you heat up a cell too much, it's just going to die, okay? It's going to cook like an egg. But you just take it a few degrees Celsius above its Goldilocks, some of the proteins are going to start to misfold. They're going to start to unravel. Some of these heat shock proteins are going to come in and help it refold back to where it needs to be so you can still maintain metabolic activity. Cold shock proteins are going to do roughly the same thing, but it's when the cell gets too cold. These will kick in, aid in, the metabolic activities, maintaining metabolic activities in a slightly colder than normal environment. Many of these are going to are going to aid in the making of cofactor containing enzymes. Nitrate reductase needs molybdenum. Well, it turns out chaperone proteins are going to help bring in the molybdenum and then get it introduced to nitrate reductase. You've seen pictures of this bullet-shaped thing. The misfolded protein will get fed down into it. And this is a collection of proteins themselves. So what they're going to do is the R groups from the amino acids of these proteins are going to interact with the R groups of this one, and they're going to push and pull and get it to fold. It's an energy-dependent process. If it can't fold, it gets targeted, it gets recycled. I forget what B is here. Oh, a cofactor. So I'm not going to sit there and worry about that.